Okay, today we will be continuing with derivatives, but we're going to be learning about some basic differentiation properties, or in other words, some shortcut rules for taking derivatives. So these are exciting. They're going to save us from having to do the four-step process for every problem that we need a derivative for. Okay, in the last section, we defined the derivative to be the limit as h goes to 0 of the difference quotient if that limit exists. And that is the same thing, but people over the years have found shortcuts for doing this because there are a lot of patterns that exist. So we talked a little bit about notation to be sure you're comfortable with all this notation here. Mainly the first three, f prime, y prime, and dy dx will be the ones that you'll see used the most. Okay, so our first rule is that if our original function is a constant, and by constant we mean just some kind of numeric number, then the derivative of that is 0. Okay, so in other words, y prime is 0, dy dx is 0. So as long as it's a constant, the derivative is going to be 0. So if we look at this, if our original function is 7, then the derivative of that would be 0 because 7's a constant. Okay, same thing here. 10, this doesn't look as much like a constant, but pi is a constant. So 10 pi squared is actually, the derivative of that is going to be 0 because, again, this is a constant. Okay, so I got something for you to practice here, and there's not a lot of practicing to do. Basically, I just want you to see that this is a constant, so its derivative is 0. So kind of keep the same notation that it starts you with. So if it's starting with you with f of x, then you want to write f prime of x. Here, y is equal to 12. So the derivative of that, because it's a constant, is going to be 0. This one has a radical in it, but it's still just a constant. So it's asking for dy dx this time. So dy dx is 0. Same thing here, the derivative of negative pi with respect to x. This is a constant, so that derivative is 0. So this rule, while beneficial, there's not a lot going on with it. Okay, the power rule is where it gets a little bit more exciting. So anytime we have a function that's x to some power, and that power could be an integer, it could be a fraction, it doesn't really matter, but as long as it's x to some real number, then it's called a power function, and the power function actually has a special rule for taking its derivative. So the derivative of any power function is going to be n, so that original power is going to come down in front, and then we're going to take 1 from the exponent. Okay, so we're going to decrease that exponent by 1. So if we look at some examples, like this one here, okay, this is n, so n is 6. So what it tells me is that the derivative of that, I'm going to bring that 6 down as a number in front. I'm going to write my x, and then I'm going to take 1 from the exponent. So 6 minus 1. So it's going to be 6x to the 5th power. Okay, let's say you have one like this. Okay, this is actually not a power function as it's written here. So what we need to do is we need to do a rewrite. And a lot of people confuse rewrites and applying the rules. A rewrite is just writing it in a different form. So if you have x to the 5th and it's in the denominator, what we can do is we could rewrite that as x to the negative 5th power. So by bringing it up, it changes to a negative exponent, okay? In this form, we can't apply the power rule, but in this form, we can, okay? So f prime of x, if I'm going to take the derivative, this exponent is going to come down in front. Okay, so I'm going to have the negative 5 in front. I'm going to have an x, and then I'm going to subtract 1 from this exponent, which is a little bit tricky here because that's going to become x to the negative 6th. So while I'm not going to take off if you leave it in this form here, I would prefer that you write it with positive exponents. So I'll probably give you like a bonus point or something if you'll write it with a positive exponent. So the -5 is fine because that is a coefficient, okay? It's only the exponents that are a problem if they're left in your answer. So we want to move whatever base is being raised to that exponent, that negative exponent, move just that base down, okay, and it'll become a positive exponent. Okay, we've got this one here. This is one for you to practice on. Okay, if we're going to take the derivative of this one, this is a power function, so I'm going to bring the 5 down in front, and I'm going to take 1 from the exponent. And you certainly don't have to keep writing this because you'll learn to do these pretty quickly. So 5x to the 4th. Okay, here's some more for you to practice. I would certainly say pause and give it a try. All right, for part A, if I'm going to take the derivative here, I'm going to bring the 6 down, x, subtract 1 from the exponent, and it would be to the 5th power. And I think that might be one we already did. B, if I'm going to take the derivative of b, I'm going to bring that exponent down as a coefficient, and I'm going to decrease that power by 1, so it's going to be to the 29th. For c, if I want dy with respect to the variable t, this is in a form I can use here. I just need to bring the -2 down as a coefficient. And then I do need to decrease that power by 1. So -2 minus 1 will be -3. I'm going to leave that -2 where it's at, but the t is what has a negative exponent. So I'm going to bring that down, and that's going to be my answer. And then it's a little hard to see, but this is the 3/2 power. So if I'm taking the derivative of this, I'm going to bring that 3/2 down as a coefficient. And then I'm going to subtract 1. So if I take 3/2 and I take 1 from it, that's actually going to be equal to 1/2. You could, if you are good at converting these, recognize that that is the square root of x. Okay, if we look at this one, when we have these power functions, you have a radical, again, you need to do a rewrite before you can take the derivative of it. So if I'm going to rewrite this would be x, and then what we do is we do the power over the index. Okay, so that means that the power is 3 and the index is 4. Okay, so this would be written as x to the 3/4. Now keep in mind that's the original function, that's not the derivative. So now we can take the derivative. Okay, so the derivative is going to be, I'm going to bring that 3/4 down, x, and then take 1 away. So 3/4 minus 1 is going to give me the -1/4 exponent. Okay, and if we want to write it with no negative exponents, then we're going to leave the 3 where it's at and the 4 is in the denominator. And I'm going to bump this x down and make it a positive exponent. Okay, if we're going to practice with these, again, feel free to pause and practice. This one here, we would need to rewrite it before we could do anything with it. So we'll rewrite it as x to the -1 because it's to the +1. If we move it up, it's going to become a -1. So then the derivative for this one The power is going to come down as a coefficient, and then I'm going to subtract 1 from my exponent, which means it'll be to the negative 2 power. So that would be negative 1 over the x is what's raised to a negative exponent, so I'm going to move it to the denominator. So negative 1/2. Negative 1 over, sorry, negative 1 over x squared. Okay, this one we want to rewrite first. So when we rewrite it, we're going to do the power over the index. And then the derivative itself, that exponent comes down as a coefficient. Take 1 away, so 2/3 minus 1 would be negative 1/3. And we want to write that with positive exponents, so that u is going to get bumped to the denominator. Only the u, not the 2, just the u. And so that's going to be to the 1/3 power. All right, and then the last one here, we do need to do a rewrite on this one. So this would be 1 over x to the 1/2. Anytime we have a square root, that's the 1/2 power. We still don't have it as a power function yet, so I need to bring this up. So it's going to be x is going to be on the top, but it's going to be a negative 1/2 as its exponent. So that's the rewrite. The actual derivative itself is going to be, I'm going to bring that down, the exponent down as a coefficient. And then I'm going to take 1 away from that existing exponent. So that would be to the negative 3/2. So negative 1 over 2, bump the x down to the denominator, and that would be our answer. Okay, our next property says that if we have a function that's actually a constant times another function, then we can find its derivative by just multiplying the constant times the derivative of that function. Okay, and that sounds like a lot. I think you'll understand in a minute that it's not as complicated as it sounds. Okay, let's say we have this and we want to find the derivative. Well, what our derivative rule tells us is that, so we have, this is our k and this is our function here, okay? So it tells us that the derivative is just the k times the derivative of this function that's left here. Okay, so the 12 times the derivative of x to the 4th. So 12 times the derivative of x to the 4th is, bring the 4 down, x, decrease the power by 1. Okay, so 12 times 4 is going to be 48x to the 3rd. I will say, as you get comfortable with this rule, what you'll see is that you actually, when you bring that 4 down, it automatically multiplies to the 12. So 4 times 12 is 48, and then you just decrease the power by 1. So that's just kind of a quicker way to do it. Okay, here's some for you to try if you feel ready. Okay, for part A, if we're going to find the derivative of that, it's going to be 4 is our constant, so it's going to be 4 times the derivative of x to the 5th. Okay, so 4 times, that's going to be 5x to the 4th. So my final answer is 20x to the 4th. For part B, I'm going to rewrite this first. Okay, so this would be like 1/12 t to the 4th. Okay, so it's like this is my constant times the t to the 4th. So the derivative of it is my constant times the derivative of t to the 4th. Okay, so that's going to be 1/12 times the derivative of t to the 4th would be 4. Bring the 4 down, t, decrease the power by 1. So I'll have 4 over 12, which is 1/3. And then I'm going to have t to the 3rd. All right, for C, we've got Okay, we need to do a rewrite. Okay, so this is going to be, y is going to be 1/3. The x is the part that's the problem. The 3 is fine. So when I move this up, it's going to be x to the -3rd. Okay, so then the derivative is going to be the 1/3. And then I'm going to take the derivative of the x to the -3rd, which would be -3x to the -4. Okay, so I bring the -3 down and I decrease the power by 1. So these 3's can cancel. I'll have -1x to the -4 or -1/x to the 4th. Okay, the last one here, we definitely need to do a rewrite on this as well. So we'll have 0.9 and then we're going to have x to the -1/3. The 1/3 comes from the fact that we do the power over the index. And then since we need to move it up to the numerator, that's why we get this. So when I take the derivative of this, I'm going to have my constant multiple, and then I'm going to multiply it by the -1/3 is going to come down as a coefficient, and then I'm going to have x, and then I'm going to decrease it by 1 and have -4/3. So 0.9 times -1/3 is -0.3, and you can check that on your calculator, and then over x to the +4/3, because we've got a negative here, we'll move it to the denominator. Okay, looking at this one, this just says that if we have two functions that make up another function that are added or subtracted together, then their derivatives are added and subtracted together as well. So what that means is if I need to find the derivative of this expression that's actually just two things added together, I'm going to find the derivative of this one, the derivative of this one, and then add them together. So the derivative of this one, I've got the 3 as the constant, and then the derivative of x to the 3rd is going to be, bring that 3 down, x, and then decrease the power. Over here, it's going to be my constant multiple, and then I'm going to bring the 2 down, and then I'm going to decrease that power. Okay, so 9x² plus 22. All right, some to practice with here. Okay, if we want to look at the derivative for this one, I'm going to have the constant times the derivative of x to the 4th, which will be 4x to the 3rd minus 2, and then times 3x² plus, this one will be 2x to the 1st. The derivative of 5x is just 5. And if you're not sure about that, like you'll bring that 1 down, so it'll be -5 times 1x to the 0. But anything to the 0 is just 1, so it becomes just the -5. And then here, the derivative of 7, that's a constant, so that's going to be 0. So when we simplify this, we'll have 12x to the 3rd minus 6x² plus 2x, and then minus 5. Okay, the derivative on this one, on part B, the derivative of a constant is 0, and then the derivative here, we've got a constant multiple, so that's going to be -7, and then the derivative of the x to the -2 would be -2x to the -3, because we've got to subtract 1 from the exponent. So we'll multiply those together, and we'll get 14x to the -3, or 14 over x to the 3rd. All right, this one we need to do a bit of a rewrite. The first term is fine, but this second term, we need to write it as the power over the index. So when we go to take the derivative of it, we'll have our constant multiple times the derivative, which would be 3v to the second. Don't switch up variables. Whatever variable they start you with is what you need to continue the whole problem with. So 15v to the second minus 1/4 v to the negative 3/4, because you're going to do 1/4 minus 1 will be negative 3/4. So that will be 15v squared minus 1/4v to the 3/4. All right, and the last one here, we've definitely got some rewrites to do. This would be negative 3/4, and then the x needs to come up, so it would be x to the negative 1. And then here we're going to have plus 4x to the negative 3, and then minus 1/8 x to the 4th. So the only things that's really a problem are when the x's are in the denominator. It's okay that the 8 is in the denominator, just treat that like a fraction. But when the x's are in the denominator, you can't do that. Okay, you've got to rewrite those. All right, so dy dx then is going to be the derivative of this. So have my constant multiple times the derivative here would be negative 1x to the negative 2, and then plus 4 times negative 3x to the negative 4, because I'm bringing that down and subtracting by 1. And then this will be negative 1/8 times 4x to the 3rd. Okay, so here I'm going to have positive 3/4 x to the negative 2. Here I'm going to have negative 12x to the negative 4. And then here I'm going to have negative 1/2 x to the 3rd. And I'm going to come back up to the corner up here to finish this since I'm out of space. So I'll have 3/4. And then the x down here is going to bump to the denominator. Minus 12. The x again is going to bump to the denominator. And then this term, this one here, I don't really have to do anything to it. Okay, and so that should be our answer for the last one. Okay, sometimes we need to rewrite, like we've already talked about some rewrites, but this is another type of rewrite that we might need to do. So we don't have at this point the rules for dealing with something like this. So what I want you to do is, sometimes I refer to this as the rabbit ears, but basically it's just taking each part and placing it over the denominator. So if you have a single term in the denominator but multiple terms in the numerator, then you can do that. You can split it up. So this would be 3 over x to the 6th. And then this one's going to be x to the 3rd over x to the 6th. Okay, so I'm going to simplify this one here. That'll be x to the negative 3. And this one's going to be 3x to the negative 6. Just bringing it up. Okay. All right, so we rewrote it. Now we can take the derivative. So the derivative then is going to be that constant multiple, and then the derivative here, which would be negative 6x to the negative 7th. And then here I'm going to bring the negative 3 down, and then I'm going to decrease the power by 1. So this would be negative 18x to the negative 7th plus 3x to the negative 4. Or if we rewrite it, it'll be negative 18x to the 7th plus 3 over x to the 4th. All right, here's one for you to practice with. Okay, if you see one like this, again, a single term in the denominator, multiple terms in the numerator, then I would say rewrite it, split it up, and you can do it like you're just going to put each part over that denominator. So 5 over x minus 3x over x plus 4x squared over x. This one I'm going to rewrite as 5x to the negative 1, bringing that x up. Here my x's will just cancel and leave me with 3. And then here I've got just a 4x. So that's still my original, not the derivative. So now I need to look at what's the derivative. Okay, so I'll have that constant multiple, and then the derivative of x to the negative 1 would be negative 1x to the negative 2. The derivative of a constant is 0, and then the derivative of 4x would just be 4. So I end up with negative 5 over x squared plus 4. All right, the last thing, you really can't do calculus without talking about velocity and acceleration just a little bit. So if we're talking about velocity, the instantaneous velocity, that's just another word of saying the derivative, okay? So we want to find the instantaneous velocity, so we want to find the derivative of this expression. So the instantaneous velocity is, like I said, the derivative. Okay, so that derivative is 3x squared minus the constant times the derivative of x squared and then plus 9. So 3x squared minus 12x and then plus 9. Okay, so using the same expression here, we just found that our derivative is 3x squared minus 12x plus 9, and we want to find the velocity at 2 and at 5. So that means I'm going to find v of 2 and v of 5. So to do that, we know that the derivative is the velocity, so I'm going to plug it into the derivative, not the original. So I'll have 3 times 2 squared minus 12 times 2 plus 9, and that's going to give me negative 3 feet per second. And then here I'm going to plug the 5 in, and that'll give me 24 feet per second. All right, so working with, again, this same equation here, our derivative is 3x squared minus 12x plus 9, okay? And we're asked to find the time when the velocity is 0, okay? So we know that the derivative is our velocity function, so we want to know when all of this is equal to 0. Okay, so what we need to do is to solve this quadratic, and this one's actually factorable. If I take a 3 out, it's going to leave me with x squared minus 4x plus 3. And then when I factor this further, I need the numbers that multiply to give me 3 and add to give me 4. So that would be minus 3 and minus 1, just factoring that. Okay, so we're going to set each factor equal to 0. Okay, so I'm going to find that at 3 and at 1 second, that's when the velocity is 0. Okay, last problem, just one for you to practice with. So if we want to find the instantaneous velocity, that's going to be the derivative. Okay, so the derivative here is 3x squared minus 15 times 2x plus 72. So that's going to be 3x squared minus 30x plus 72. Okay, so we need to evaluate this at the velocity at 2 and also the velocity at 5. So that's going to be 3 times 2 squared minus 30 times 2 plus 72. That's going to be 24 feet per second. And then if we evaluate this one, we're going to get negative 3 feet per second. So that would be the velocity at those specific times. And then part C, we want to find the time when the velocity is 0. So my velocity equation is this 3x squared minus 30x plus 72. So we want to find when it's equal to 0. So I'm going to take 3 out. As a GCF. And then when I factor this, I need numbers that multiply to give me 24 and add to give me 10. So I'm going to do 6 and 4. So when I set those equal to 0, x minus 6 equals 0, and x minus 4 equals 0, I'm going to get 6 and 4 seconds. So at 6 seconds and at 4 seconds, the velocity would be. Okay, looking at this one, we want to find the equation of a tangent line. We did this back in the previous section, but it's much easier now. So the derivative here is going to be, I'm going to have 3 times, this would be 3x squared minus 2 times 2x, and the derivative of 5 would be 0. So that's going to be 9x squared minus 4x. Okay, so we want to, and that says find the derivative, which was the first thing we did. Okay, and then the second part is we want to find the equation of the tangent line for x equals 1. So before, when we did this, we said to write the equation of a line, you've got to have a slope. Okay, so we want the slope of the tangent line. Right, so I'm going to get that by finding the value of the derivative when x is 1. Okay, so I'm going to plug 1 into the derivative. So that'll be 9 times 1 squared minus 4 times 1 would be 5. Okay, and then I need a point. Okay, so that point is going to be the x that I want, which is 1, and then f of 1. So I'm going to plug 1 into the original function. Okay, so that would be 3 times 1 cubed minus 2 times 1 squared plus 5. So 3 minus 2 plus 5 is going to be, it looks like 6. All right, so we're going to do y equals mx plus b to finish this up, since we have the slope and we have the point. So 6 is equal to m, which is 5, x is 1. We don't know the b, so I'll subtract the 5 from both sides and get b equals, okay, so we'll have y equals 5x plus 1. All right, and last, find the values of x where the tangent line is horizontal. Okay, so in order to do that, we basically need to know where the slope is 0, because that's where we would have a horizontal tangent line. So our derivative we've got is here. So we want to see when that derivative is equal to 0. Okay, so we're going to look and see when 9x squared minus 4x is equal to 0. So that'll be, if I factor out an x, that's going to be 9x minus 4. So we've got two factors here. So when x equals 0, we have a horizontal tangent line, and then when 9x minus 4 equals 0, we have a horizontal tangent line. So that means when x is 4/9. All right, here's one for you to practice with, same steps that we just went through. So our derivative on this one is 4x to the third minus 8 times 3x squared, and then that's going to be 0 for that derivative. So 4x to the third minus 24x squared. The equation of the tangent line at x equals 1, we know we need the slope of the tangent line. So that's going to be the derivative at that point of 1. So 4 times 1 to the third minus 24 times 1 squared. So 4 minus 24 would give me negative 20. And my point, that's going to be 1 and f of 1. Okay, so 1, and then if I plug 1 in up here, 1 to the fourth is 1 minus 8 plus 7. So that's going to be 0. So we've got the point 1, 0. So we'll have y equals mx plus b. So 0 is y, m is negative 20, and x is 1. So that means b is 20. So we'll have y equals negative 20x plus 20. And then last, we want to find the values where the tangent line is horizontal. So that means where f prime of x is equal to 0. So we're going to take the 4x to the third minus 24x squared, set that equal to 0. So we'll factor out a 4 and an x squared. So we'll end up with, if we set that equal to 0, we're going to get x squared is equal to 0. And then here, we're going to get x equals 6. Okay, one business application here. You've got a company's total sales are given in this equation here. You want to find the derivative and then interpret those. So if we look at this, obviously the first derivative is pretty easy to find, even though there's some decimals in it. You should just be able to apply your regular rules. So the first one, it asks you to evaluate it at 5. Let's just plug in 5 into the original function. This is plugging 5 into the derivative. So basically, as far as interpreting these, so after 5 months, because that's where the 5 comes from, that's your number of months that have elapsed, sales are represented by the original function. Okay, so if you plug 5 into that, you're going to get the 29.25. This is in millions of dollars. So that's how many millions of dollars you would have expected to have sold after 5 months. And then here, this is the derivative. So this represents a rate of change. So basically, how fast is the sales changing? So they're changing at $9.25 million, and that would be per year. Okay, so it is important to get your units right. So when you're talking about the derivative, it's a rate of change. So your units are going to be not just millions of dollars, but millions of dollars. And I said per year, but it should have been per month. So $1 million per month is how much your sales are changing.